Okay, guys, ready for some action? So today I'm going to kind of review everything we have done in ODEs. And to start with, let me actually give you an equation to work with. An example of equation where kind of integrates everything we have learned. So I'm going to write down the equation. I would like you to choose a time integration method we have learned. Okay, and pick a time step, pick a delta t, and try to figure out solve this equation either on your computer, or if you don't have a computer with MATLAB installed, you can either find a partner or work out the scheme on paper, and then I can type it in my computer. All right. So the equation I'm asking you to solve is called the Van der Pol equation. The Van der Pol equation is named after Van der Pol, who is an electrical engineer. So he devised the equation to explain some punctuated equilibrium he observed in electrical circuits. And the equation is like that. So the second derivative of u is equal to minus u. So if I just stop over here, anybody realize what kind of equation this is? Huh? If it's du dt equal to minus u, yes, it is an exponential. But here I have the second derivative of u equal to minus u. How does that behave? Sine and cosine, right? This is a harmonic oscillator, right? A second derivative, like the acceleration equal to minus position, right? But there is a little bit more. So the additional stuff is plus a mu, a damping coefficient, that's the additional parameter, and 1 minus u squared times du dt. Okay, so this is the additional magical term. As you can see, when mu is very small, the equation should behave pretty much like an harmonic oscillator, right? So here we are looking specifically in the case where mu is large. So let's set mu equal to 1,000. It's not huge, but like pretty large. So that's the equation. Okay, what's the first step when you look at this equation, when you want to look at numerical solutions? First of all, I can guarantee you wouldn't be able to find an analytical solution in class. I mean, mathematicians has been tried for decades, and no analytical solution yet, so you can give up on that. Okay, and for numerical method to solve it, how do we start with this equation?
Could you expand the second derivative so that it's in terms of the first?
Yes. First of all is to convert this second order differential equation into a set of first order equations. Therefore, talking about the system of equations, this looks like a single equation, but when you want to solve it numerically, it is actually equivalent to a system of first order equations. And then we can start solving it. So here, let me just write the equation out for you. I'm going to define v as du dt. Okay, then the derivative, the first order derivative of, let me just write out this factor of u and v is equal to the derivative of u is already defined as v, so the first line is v, the second line is minus u plus this mu. Let me just write 1,000 times 1 minus u squared times du dt, which is v. Okay. All right. Let's start from here. We have learned forward order, midpoint, and our second order Runge-Kutta scheme, right, which we discussed last lecture. So all of these schemes are zero stable, and we know their order of accuracy. They are first order, second order, and second order, right? So the only thing you have to do to pick out one from these schemes is what? We have discussed what qualifies as a good ODE scheme, right? It has to be accurate, has to be zero stable, which we know they are, and long-term stability, right? Okay, so the only thing you have to do to figure out which scheme is suitable is to do long-term stability analysis. Okay, so how do you do long-term stability analysis to equations like that? The eigenvalues, right? So if you have a system of equations, you can write a matrix, d vector dt equal to a matrix times that vector. Then you can do eigenvalue analysis to the matrix. But where is the matrix here? Where is my matrix? Yes? Where's my matrix?
You can express the right-hand side of the equation as a matrix times column vector UV.
Right. So let's try to write it as a function of a column vector UV, a matrix function of UV. So what is the first row of the matrix? 0, 1, as always, right? When we expand a second order ODE into a system of ODEs, the first row is always 0, 1. How about the second row? -1. Yeah, a mu, which is 1,000 times 1 minus u squared. Okay, so now we have a matrix, right? But the matrix depends on u. So we can kind of randomly plug in a few u values and try to figure out, actually the stability is going to be different when the solution are experiencing different periods of time, right? So the solution u is going to change, therefore the matrix is going to change. But let's actually do some analysis to this matrix, plug in some random values of u, and try to figure out what's the stability properties of this system. And therefore, let's go ahead and choose a ODE integration scheme for this. All right. So if you have MATLAB, you can use the eigenvalue function to try it on this matrix. If you don't have MATLAB, or you prefer hand calculations, you can also plug in some convenient values of u and tries to hand calculate the eigenvalue. It's not that difficult. All right.